So in the last video, we looked at introducing the idea of dynamics, and we kind of restricted ourselves to just one dimension. So a single number, whether positive or negative, would tell you where you were along that one dimension. We did a few interesting problems. Mostly this dealt with the ideas of average, instantaneous velocities and accelerations, and the use of integration and differentiation to arrive at how these quantities change with time. Okay, so let's now extend our discussion to planar motion, where now instead of restricting ourselves to motion in a single dimension, we restrict ourselves to motion within a plane. And so in this case, if this here is a coordinate system that allows us to talk about um, points on this plane, if you have some point as, say, this point here, which is at a distance of x1 from the y-axis and y1 from the x-axis. So this here is y1, this here is x1. Now, as this point, as it changes, as it moves with time, at any instant of time, if you want to know its location, all you need are its coordinates, that is xi, yi. Okay, and anytime that you have these ordered sets of information, so in this case the first is xi, the second is yi, this sets up the idea of a vector representation. So a vector x1 y1 will be defined as this vector here, and some x2 y2 that refers to this point here would be a vector here. Okay, so to be able to talk about this, let's quickly review the idea of vectors. Vectors are quantities with both magnitude and direction. This is a very general definition. Sorry. I guess to be more specific, it has to be a defined or a single dimension, one direction. Now, in this definition, the magnitude is some non-negative scalar, which is basically giving a sense of distance. So this, if you were to measure it, how much is this distance? That is a magnitude. And this distance is non-negative, which means that it can be 0 or some positive number. And the idea of scalar means essentially that it is some number which possibly has units. So something like 1 meter is a scalar. So that is for distance. 35 degrees Fahrenheit is a scalar for temperature. Okay. So that's the idea of a scalar. Now, non-negative means that it must be greater than or equal to 0. So the magnitude must be greater than or equal to 0. And then there's only one direction. So in this case, the direction sense is in this direction. What are some examples of vectors? You could have forces, velocity, displacement. All of these are possible examples of vectors. Now, how do you represent it? So we kind of already drew a vector here. So that is one way of representing it. So this here is a vector. Let's say this is a vector. It is possible for you to move this vector so long as you keep its magnitude and direction same, it is still the same vector. Okay, so you can translate it in any way you like. So long as its magnitude and the direction are the same, it's still the same vector, which means if I had to move it in this way, there's still the A vector. Okay, and some things about the parts of a vector. This here is called the tip, and this here is the tail. Now that becomes important soon when we start discussing ideas of angles and so on. So this here is a vector representation. And what I just showed over here is that vectors can be translated without rotation or change in magnitude. And they remain the same. So here, this vector and this vector are the same, or they are equal vectors. Okay, so there's one representation. Now, another representation is if you're not able to show your vector in the same plane in which you're drawing it. For example, what if the vector was pointing perpendicularly outward versus perpendicularly inward to the plane that you're drawing? How would you do that? Some of you might have already encountered this, but if you draw a vector in this way as a curled arrow, or in this way, they have an inherent sense that is shown. Okay, and this sense, it relates to using your right hand to determine what direction is this arrow pointing. Okay, I will tell you what that is. So you use your right hand and you hold it as a thumbs up symbol. Um, so your outside of your thumb, all the other fingers are curling. Now you want it to be such that the curl of your fingers matches the drawn curl of this vector arrow. And in this case, you can see that the one on the left, that is this one, if you were to curl your fingers of your right hand in this way, then your thumb is pointing outward, right? Take a moment to do this yourself. So the one on the left is pointing outward. You're taking the fingers of your hand, curling them into this, as I've shown here, this image. And in doing so, you can see that your thumb is pointing outward. That's the direction of this vector. So it's a vector that's pointing outward from the plane that it is drawn. The same way, if you were to do it for the one on the right, your fingers will curl in this direction and your thumb would be pointing inward. Okay, and so these are alternate representations of vectors. So there's the right hand rule. Okay, so I hope this stuff is making sense. Now, we talked about the magnitude. Um, for this vector here, the magnitude is essentially this distance. Okay, and that is represented by, so the magnitude is represented by this. And that gives you a sense of the magnitude of this vector, which is like how much of a distance or how much of a magnitude of force is being conveyed by the vector. What about the direction? So the direction is denoted by unit vectors as A. In this case, we're doing A vector, right? But instead of the rightward arrow, you would show this hat. So A hat, okay? Unit vectors, they act as signposts for direction sense. and they have a magnitude of 1. Okay. Um, so, for example, you could think of talking about the northward direction. So, that is uh, only defining a direction. It's not really telling you a magnitude. So, if you were to say that you have to go 8 miles north, now that has both magnitude and direction, and that can be represented as a vector. Okay. So, some unit vectors that you're familiar with are maybe I hat is a unit vector. Of course, there's magnitude 1 aligned along the x-axis. There's a general convention. Similarly, j hat is aligned along y-axis, and k hat is aligned along z-axis. Okay, so this is familiar. Um, Other representations might also be something like n x hat. So this is in the reference frame n. This would be along the direction of x according to that reference frame. This would be ny hat or nz hat. All of these are direction senses. Okay, so if you do have the magnitude and the direction sense, we can then say that a vector is the magnitude of a and it's in the direction of a hat. Okay, so this is still quite general in the sense of directions, sorry, in the sense of vectors without really talking about reference frames and so on. Um, this could also allow you to write that the direction sense of any vector is simply that vector divided by its magnitude. Okay, can we divide two vectors? No, it doesn't make any sense. But this here is a vector and this here is a scalar. So you can divide a vector with a scalar magnitude. And so this here gives you a new vector which has a magnitude of 1 and the direction will be along this vector that you're interested in. Okay, some more definitions. A zero vector. This here is a vector which has a magnitude of 0. But since it is a vector, it still has a direction. It's just that that direction sense is undefined. It is lost. Okay, how does that happen? It's when you have done some product or some addition subtraction such that that vector has now become 0, but it still remains a vector, and because of that, it has some direction that is undefined in this case. So this is okay. With that, let's move on to some definitions of vector operations. So if you have a vector here is a vector and you have some other vector as say b vector and you wanted to add them together, then you want a vector plus b vector. To do that, you need to have the tip of one of the vectors touching the tail of the other. Okay, and so if I were to now translate this here, now I can draw what is a vector plus b vector. What if I were to do b vector plus a vector? Okay, let's see about that. So I'm trying to do b vector plus a vector. That is still tail of one is touching the tip of the other. And if I were to draw the resulting vector that's shown here, this here is the same A vector plus B vector. You can see that the direction is the same and the magnitude is also the same. And this kind of leads us straight to one of the properties, which is the commutative property, which essentially states that A vector plus B vector is the same as B vector plus A vector. Okay. Well, I guess to make this concrete, I should have written this as B vector plus A vector. So this shown here is vector addition. And then you have vector subtraction, wherein if you had the same A vector and B vector, but now you wanted to do A vector minus B vector, then you have to draw B vector in the other direction sense, that is in this way. You have the same magnitude and the opposite direction. This here is minus B vector. And now what do you have? You have A vector minus B vector, which then gives you this guy here. As A vector minus B vector. So does this vector here have a negative magnitude? No. You have to keep in mind that vectors always have a non-negative scalar magnitude. So when you're actually doing this operation here, you're changing the unit vector of B, you're just changing the direction. So you're assigning a negative to all the components of that unit vector. And this process is actually called vector negation. Wherein you take one vector, B in this case, and you get the negative of that. And the important thing to note here is that the magnitude of minus B vector is still positive. Well, I should be more specific. Instead of positive, I should say still non-negative. It's never negative. It just reverses the unit vector. Okay. This here is some specifics about the vector operations. Now we can just list out some of the properties. The associative property. Try to recall what this is. This basically just says that A vector plus B vector plus C vector is equal to, you could do the first operation first and then the second. Or you could do A vector plus C vector plus B vector. So you can do this first, or you can do this first, or you can do this first. It's all the same. Okay. So now some more operations in vector multiplication. In particular, we're going to look at scalar multiplication. This is just, you have some positive scalar or negative scalar, and if you were to assign that before your vector, then what changes would happen? So if it is a positive scalar, something like 5 or 10 or root 2 or something, it changes magnitude of the vector only. if it were a negative scalar, it changes magnitude and reverses the direction. If the scalar value is equal to 1, then there is no change at all. And if the scalar value is equal to 0, then it becomes a 0 vector, which means that if you multiply 0 with a vector, your end result is not a scalar, it's still a vector. It would be a 0 vector. So there is some direction that information is lost, but the magnitude is 0. Okay, that's somewhat straightforward. Dot products, though, start making things more interesting. If you have a vector as shown here, let's say this here is b vector, and you have some vector here as a vector. Now, to do the dot product, you need to understand what is the angle between the two vectors. Okay, so the angle between vectors is defined when the tail touches the tail or tip touches tip. So in this case, we would have to translate this here. As you know, that's the same vector. And then this angle here would define the angle between the vectors. Okay. It also requires that this angle must be between 0 and 180 degrees. Okay, so essentially it is this, it is not this. Okay, so it's always between 0 and 180 degrees. Once you have defined this angle, then you can define that the dot product, which is in this case a vector dot b vector, is going to be the magnitude of a times the magnitude of b times cos of the angle between them. This here is an extremely useful operation because with this now, you have a way of obtaining the magnitude, you have a way of representing it along certain reference systems and so on and so forth. Okay, let's discuss this. We can use it to obtain the magnitude. For example, what happens if you do a vector dot a vector? It's like you have two identical vectors. They have no angle between them. And so the angle is essentially 0. This gives you magnitude of A times the magnitude of A times cos 0, which is essentially the magnitude of A squared. This means that the magnitude of A is root over A vector dot A vector. Okay, so this is one way of calculating the magnitude using a dot product. Next, you can use this clearly once you have the magnitude. You can then define the unit vector along any vector A is simply A vector divided by the magnitude, right? Which we know is root over A vector dot A vector. Of course, if there's some way for you to find out what is A vector dot B vector, so if A vector dot B vector is known and magnitude of A and magnitude of B are known, then you have that cos theta is equal to a vector dot b vector divided by their magnitudes multiplied, right? So now you can find theta as cos inverse of this. If in particular a vector dot b vector is equal to 0, then you have by definition that cos theta has to be 0, which means that a vector is perpendicular to b vector. Okay, I guess a caveat is that a vector and b vector are not zero vectors. If their magnitudes are 0, then of course we can't really say this. If instead a vector dot b vector is equal to the magnitude of a times the magnitude of b, then what can you say? Cos theta is equal to 1, which means a vector is parallel to b vector. And if instead a vector dot b vector is minus the magnitudes, then cos theta is equal to minus 1, which means the angle between a vector and b vector is 180 degrees, which means that a vector and b vector they're called anti-parallel. Okay, so that was a lot of vector relations. Now let's make use of this in the sense of using reference frames. So if you have that there is some vector given by u vector, and you have another vector that is v vector, and you have some reference frame that's defined as shown here. So you have I hat and j hat. Now you can obtain your vector u as components along the I hat and the j hat direction. So you could write that this here is ux I hat, and this here is uy j hat, right? You're familiar with this? This here is vx I hat, and this here is vy j hat. So if you then have that u vector is equal to ux I hat plus uy j hat, and v vector is vx I hat plus vy j hat, then you can write that u vector plus v vector is, and you're just adding these together. So it'll be ux I hat plus vx I hat, or you can collect them in this way. And now you can find the magnitude of this as the magnitude of u vector plus v vector is equal to, and you know this is the dot product of these. So it's u vector plus v vector dot with itself, whole thing under root. What happens now? If you were to do the dot product, you then get ux plus vx I hat dot, and then you have ux plus vx I hat plus uy plus vy j hat, plus you have the same thing from the y direction, that's uy vy j hat dot, and then the same thing, right? So this is like the distributive property. What happens now? You have I hat dot I hat, so it's I hat in with itself that has magnitude of 1 and cos 0 is 1. So this remains as ux plus vx whole squared because these two are magnitudes. I hat dot I hat is 1. If you were to do this, you then have I hat dot j hat, which is 90 degrees apart, which means its cos 90 is 0. So that vanishes. And then you have, for the second part, uy plus vy. If you were to do j hat dot I hat, it vanishes. This remains. And so you will then have the square of that. So the reason why we're able to write that the magnitude of a vector is its components, the sum of the square of its components under root is only when the unit vectors that are being defined are perpendicular to each other. Okay, if that was not the case, then we would have to account for the direction sense. Sorry, the direction between the unit vectors, if there was some theta. I believe we're going to do a problem that's related to this directly. Okay, with that, let's quickly do a problem where we have two unit vectors uh, such that the angle between them is 60 degrees. So ST means such that the angle between them is 60 degrees. And we're now using this reference frame. Okay, so we have some vector. A vector is 3v hat plus 2u hat. Another one is B vector is 2v hat plus u hat. Is this allowed? Of course. You can define any vector as um, using any kind of unit vector as a basis. This here is u hat, this here is v hat, and the angle between them is 60 degrees. So a vector is you moving along this. So you have three of these. Well, sorry, you have two along this, and then you have three along v hat. So this here is your a vector. And similarly, your b vector is 2 times along this and 1 time along this. This gives you your b vector. Now the question asks you for what is the magnitude of a vector plus b vector. You can pause the video and try to obtain the answer yourself. Okay, so I'm gonna discuss the answer. So this is square root of a vector plus b vector dot a vector plus b vector. If you now had done the addition, you would have this is 5v vector, sorry, 5v hat plus 3u hat dot with itself. Right? A vector plus b vector is 3 plus 2 along v hat and 2 plus 1 along u hat. And if you do this now, you will obtain square root of your 5 times 5 v hat dot v hat is 1, so you have 25, plus you have 5 times 3, that is 15 v hat dot u hat, and then you have 3 times 5, again 15 u hat dot v hat, plus 9 u hat dot u hat, that's 1. Which essentially gives you 9 plus 25, that is 34, plus 30 times u hat dot v hat, which is the same as v hat dot u hat, as you can see. It's independent of the direction. You're just a vector dot b vector is the same as b vector dot a vector. It's just you will flip this direction order. It doesn't matter. So here you have u hat dot v hat, which is just square root of 34 plus 30 cos of the angle between them, that's cos 60, which should give you cos 60 is half. So you get square root of 34 plus 15, that is square root of 49, that is 7. Okay. Um, can you now do a vector dot b vector? So you'd have 3v hat plus 2u hat dot 2v hat plus u hat, which then gives you 6 plus 2, right? So 3v hat, 2v hat, so that is 6. 2u hat, u hat, that is 2. And then you have 3 times 1 v hat dot u hat, and then you have 2 times 2 u hat dot v hat. And you know that this here is cos 60, that is half. There's also cos 60, that is half. In the end, you will get the answer as 11.5. Okay, so clearly, if we have an angle between the unit vectors and using this as a way to represent your vectors, it makes your life a little more difficult because you have to account for the angle between them. Every time you have to look for that angle. Instead, when we have unit vectors that are perpendicular to each other, um, things are a lot more straightforward because anytime you have I hat dot j hat or I hat dot k hat, the dot product just vanishes. Okay, so orthonormal vectors are, well, I guess I will define it now. So orthonormal means unit vectors that are perpendicular to each other. And so using orthonormal bases as a representation of space is super useful. That's what we just found. The reason for that is I hat dot j hat is equal to 0, I hat dot k hat is equal to 0, and j hat dot k hat is equal to 0. Right, so this forms an orthonormal basis, and by convention, the directions are defined according to the right-hand rule. What does that mean? If you have your I hat in this way and your j hat in this way, then your third unit vector, that is k hat, will be in the direction defined by the right-hand rule, where you go from I to j. So a unit vector that is along this direction would be your k hat. That is your k hat. Or how you can think of this is using your right hand, have your palm aligned along the first vector such that you can rotate your palm to the second vector, and the direction that your thumb would point to is the direction of the third vector. Okay, or you can just draw from your first to the second, you draw a curved arrow to represent how your fingers would curl. We just talked about that with the right hand rule, you remember, with the thumbs up emoticon. So the direction that your fingers curl is the direction of your third unit vector. Be careful about that. It's not always as straightforward as what I drew here. For example, if I had an x hat and an y hat, So this is not the conventional direction sense, as you can see. What direction will be your third unit vector, that is nz hat? Pause and then have a look. So again, you want to go from x to y. So you have a curved vector in this way. That would be the direction of your third unit vector in z hat. So you can do it in the way that I showed, where you go from x to y, drawing a curved arrow, or you have your right hand in a thumbs up stance, and then your fingers are curling from your first vector x to your second vector y, and that gives you z. Okay. Now, why is it in the x to the y? That's because you, according to the directions of the right hand bases, you have x to y gives you z. So if you go from x to y doing this, what we just discussed, you should get z. If you go from z to x, you should get y. If you go in the opposite direction sense, you will get negative. Okay, keep that in mind. So as an exercise, you can look at the case where you go from z to x. So have your palm aligned along the k hat direction, that's z direction, and then you rotate it towards your I direction, and you will see that your thumb is pointing along the j hat direction. Okay, so this here is a right hand basis, and this is a convention that we use. Okay, so with that, let's now look at a very simple problem. Well, actually, it's not really a problem, but let's say that you have used your basis representation and you've arrived at 4t minus 2 I hat plus 3y j hat is equal to, and then you have just 2 I hat plus 6 j hat. So how do you find out what is t and what is y? The two unknowns over here. I'm pretty sure you're all very familiar with having this written down as 4t minus 2 is equal to 2, because you're matching this with this, and then you're matching 3y with 6. My question is, what operation allows you to do this? Are you doing anything special, or is it something that we've done already in this discussion so far? So essentially here you're doing a dot product with the I hat on both sides. So when you do that dot product, this becomes a scalar as 4t minus 2, and I hat dot j hat vanishes, so this becomes 0. So that's what you get here. And similarly, when you do a dot product with j hat, you get this 3y is equal to 6. So you can then obtain t is equal to 1, and in this case you get y is equal to 2. Okay, so this is something you should know. Let's just do one more thing here. Let's say we have that root p I hat is equal to 2 I hat. And you see someone doing this step. So you have root p is equal to 2 I hat divided by I hat is equal to 2. And you then get p is equal to 4. Is this okay? No, it's not, because this here is division by vectors, which is not defined. It doesn't make any sense to divide by vectors. And so this is the wrong process. If you were to do it in the right way, you're just doing a dot product with I hat, which will then get you root p is equal to 2, and that gives you p is equal to 4. Okay, so keep that in mind. Okay, um, I hope this stuff makes sense. Of course, you can always email me if you have any questions. Let's do a quick problem now, something related to calibration in robotics. Okay, so this here is a coordinate measuring machine. If you're familiar with that, the idea is that this tip over here will go and make contact with different parts of an object. So let's say you have some object, let's say it's a box, and you just place it on the bed of your coordinate measuring machine. This tip will go and contact this point here, then probably a point here, 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 here. And every point that it is touching, it will then provide you with the exact coordinate in your reference frame, which is along that bed. Okay, so to be able to do that, the coordinate measuring machine, the CMM, must be able to calibrate itself. It usually does that by going and touching some known point in your reference frame. And in doing so, it then measures what is the angle theta here, here, and you know the lengths. And so with that, you can then find out what angle configuration gives you that particular point and so on. Okay, so I took the time to write down the question. Essentially, we want to define a vector from O to this point R. We know the lengths L1, which is from this point O. It's like the origin. From O to P is distance of L1, that's fixed. From P to Q is the distance of L2, that's fixed. But this angle theta 1 can vary as this arm can rotate. Similarly, from Q to the tip R, it's a length of L3, and this angle theta 2 can change because this arm can also rotate. So we're trying to find out what is the vector from O to R. Okay, so first you can write this as R from O to R. That's wherein R is usually used for a position vector. This can also be written as vector R with respect to O. And essentially, we need to now write it in terms of the unit vector nx hat and the unit vector ny hat. Something along nx hat plus something along ny hat should give you the vector R with respect to O. Okay, so you can pause the video and try to solve this. It should be fun. You will, of course, have only L1, L2, L3, theta 1, and theta 2 in your answers. Okay, so how do you solve this? First, you want to think about what properties we can use. If you have this vector defined and this vector defined and this vector defined, then that gives you this vector, right? It's just vector addition. This plus this gives you this vector. This vector plus this vector gives you this vector. So that's how I'd approach it. I'm going to define the position vector from O to R as the position vector from O to P plus the position vector from P to Q plus the position vector from Q to R. And all we have to do now is define these these vectors. The first one is rather straightforward. So I'll write that down here from O to P. This is just L1 along nx hat. Notice here that nx hat is to the left. It's not illegal, it's allowed. So this here is L1 and x hat. What about the vector from P to Q? In this case, you want to be able to write this in terms of nx hat. So you could do L2 cos of this angle right? Where this angle here is 180 minus theta 1. So that gives you the component of this along nx hat. That is L2 cos of 180 minus theta along nx hat. And then you have some component along ny hat, which is this angle here. So you could just do L2 sine of this angle to give you the same. So L2 sine of 180 minus theta times ny hat. Now, you should be able to calculate what this is using, you can either use cos A plus B formula, and this here would be sine A plus B or A minus B formula. But there's a easier way to do this, which is using mnemonics. Essentially, these are the quadrants. So there's the first quadrant, second quadrant, third quadrant, and fourth quadrant. There's just the angle quadrants. And so this here are all angles between 0 and 90. This here is 90 to 180. This is 180 to 270, 270 to 360 in degrees, of course. So here, all that is sine, cosine, they're all positive. Here is the mnemonics part. All students take coffee is how I like to remember it. There are other ways, but in the place where students comes in, only sine is positive. Tan is positive here, which is a way of saying that both sine and cosine are negative, but the tan would be positive. And here it would be cosine that is positive. Okay, so if you have something as 90 plus theta, and you're entering this space here, so sine of 90 plus will remain positive. Similarly, sine of 180 minus will remain positive. Okay, but if you're going from the vertical axis to this, your sine becomes cosine and your cosine becomes sine. If you're going from your horizontal axis to this, your sine or cosine remains the same. Okay, so there are two aspects to it. Whether it is positive or not is dependent on this. Whether your sine remains sine and your cosine remains cosine is dependent on whether you're doing a referent from the horizontal, that is 180 minus or 180 plus. But if you're going from the vertical to some space, your sine or cosine changes direction sense. Sorry, sine or cosine becomes the reciprocal. So sine becomes cosine, cosine becomes sine. So in this case, everything is with respect to 180. So that means your cos remains cos, but you know that you're going from 180 minus theta. So only sine would have remained as positive. So in this case, it's minus L2 cos theta nx hat. In this case, you're going 180 minus, so it is still sine, but because sine is positive there anyway, it remains as positive. So L2 sine theta and y hat. If this is difficult for you to remember, you can always use sine of a minus b, and then you'll get the same answer. Here you have cos of a minus b, and you get the same answer. Okay, all of that was a review, trigonometry, really. Position vector from O to P is found, from P to Q is found. Now we need to find from Q to R. So the position from Q to R. Can we directly make use of this angle theta? No, because what you need is the angle between that vector here and this horizontal line and this vertical line. So we need to know what is this angle here. How do we find that? First, let's look at what is, um, we're trying to find this angle here. You know that this much is theta 2. Um, in this set of parallel lines, if this theta 1, then this here is 180 minus theta 1. Okay, so this is 180 minus theta 1, and this much is theta 2. So what then is this angle here? It will be theta 2 minus this angle. So it's theta 2 minus 180 plus theta 1. Or I can rewrite that angle as theta 1 plus theta 2 minus 180. Okay, so I'm now going to try to write that down. It is L3 cos of the angle that I just defined. This is along the minus and x hat direction, right? We're going in this direction, which is opposed to this. So this component here, which we just defined, is in the opposite direction since this nx hat. Okay, so there's again a review. Plus, you have L3 sine of theta 1 plus theta 2 minus 180 in the ny hat direction. So it's along this direction. Okay, now here we are again with having to deal with this. You could do a minus b, so cos of a minus b, and you could get the answer. Or if you were trying to use it in the sense of what I was doing, you will then have, meaning using those quadrants, you have that you're going um, so if there was something as theta here and this here is minus theta, cos of minus theta is the same as cos theta. Why? Because all students take coffee, which is basically cosine. Sorry. So cos of minus theta is the same as cos theta, which allows me to then write that this is minus L3 cos of 180 minus theta 1 plus theta 2 and x hat. But sine of minus theta is negative of sine theta. So I would have to write this as minus L3 sine of 180 minus theta 1 plus theta 2 and y hat. Why did I write it in this way? Why did I change it to be this way? Is because all of this is written for with reference to something. So it's 180 minus would give you everything that you have here. So let's now look at this. So cos of 180 minus theta. So you're going from the horizontal, 180 minus theta. Only sine would have been positive, which means that this here becomes minus cos of whatever angle. So since I have a minus before that, it'll be minus of minus, so positive L3 still cos 180. Well, we already accounted for that. Theta 1 plus theta 2 and x hat. And in this case, it is 180 minus theta, but now it's sine, so the sign remains same. It'll be minus L3 sine of theta 1 plus theta 2 and y hat. Okay, so we were able to write down all three vectors in a way that is useful. And then you have the position vector from O to R is just the sum of all of these, which then gives me L1 minus L2 cos theta plus L3 cos of theta 1 plus theta 2 in the nx hat direction, plus you have L2 sine theta minus L3 sine of theta 1 plus theta 2 along nx hat, ny hat. So this would be a complete answer. If your answer had these terms within it, that is improper. It would be impolite. It would not be professional. You need to have your answer completely simplified into what is representative of the information that you have. So information that you had was with theta 1, theta 2, and so on. You shouldn't have 180 minus theta 1 and so on within your answer. Okay, so that was making use of vectors in 2D. Let's now try to make use of it in 3D. Of course, if you have any questions, please do email me. Okay, so this here is now the case where you have three helicopters. They are RC helicopters and they have cables attached to them, and they are bringing this parcel. Okay, and the cables have some lengths that you have to find out. The objective is that this parcel should be located at a position that's defined as shown here. So it's 15 meters from the position below this helicopter is your second helicopter, and 12 meters from that helicopter is this one. Okay, now the problem is that they're not at 90 degrees, so they're at an angle of theta. Okay, so you have some theta angle between them, and now your objective is that the parcel must be at a height of 5 meters from the ground and at a distance of 8 meters from this line and at a distance of 6 meters from this line. Okay, so essentially you're now defining this point here based on this, and then from here there's a height of 5 meters to define where this parcel should be. All of these helicopters are at a height of 30 meters and they're all stationary. And what you have to do now is find the lengths of these cables. I'm going to give them names as X, Y, and Z. So essentially, find the lengths of the cables X, Y, and Z so that this parcel can be exactly positioned as shown here. Of course, your answers will include theta, and give it a shot. I'll now write down the full question, and I'll also provide a hint. So first, you can define unit vectors along directions that are useful to you. Unit vectors don't have to be perpendicular to each other. You could, for instance, define the unit vectors to be along these directions, as I've just shown here. That might make it easy for you. You just have to take into account the fact that between these two unit vectors, there's an angle of theta, while between these two, it is perpendicular, and between these two, it is perpendicular. So somewhat similar to what we've done here, you to account for the angle between unit vectors. Okay, so I have now written down the full question. There are three RC helicopters. They're stationary at a height of 30 meters. And as I discussed, we have all of these positions marked. The only thing is that theta is not 90 degrees, which should have made life probably easier for you. We have to determine the lengths of cables X, Y, Z. So how would you approach this? This is three-dimensional. You want to have unit vectors that are able to represent 3D space. So you will have 3 unit vectors. And you also need to have, in some way, you want to have this as a vector so that you can then define its magnitude based on the unit vectors. Similarly, the same for this one and for that one, right? So if I were to write anything down, I need to first define unit vectors. So let me say I define one unit vector this way, one unit vector in this way and one in this way, simply because most of the dimensions are already in these directions. So I could then say that this here is u hat, this here is v hat, and this here is, say, w hat. It could be anything. It's up to you. Now I want to define this vector in some way. It could be the other way as well. It doesn't really matter because the magnitude just looks at the distance. So if I now want to do that, I want to define some names for these points. So I'm going to call this as point A, this as point B, and this is point C. And this parcel here, I'm going to call it P, and I'm going to define the origin of this reference frame as O. Okay, so essentially, if I can write down a position vector from A to P, let's say, in some way, then the magnitude of this is your x. Similarly, y is magnitude of the vector from B to P, and so on. Okay, so um, let's try to write A to P in some way. How can I do that? A to P. I could write a vector from O to A, right? Because that is known as 15 along W and 30 along V hats. Can we write one for O to P? Yes, it is 8 along U hat, 6 along W hat, and 5 along V hat. Okay, so you have vectors for this and for this. What then is this vector? Well, it's just the addition of these, right? So I could write that the position from O to A plus the position from A to P is equal to the position from O to P. Okay, let's look at that carefully. This vector plus this vector is equal to this vector, right? That's what I've written down here, which then allows me to write that the position from A to P is the position from O to P minus the position from O to A. This minus that is this. Okay, so we have what is O to P. That is what? 15 W hat. Sorry. O to P is this one. So that is 8 along U hat plus 6 along W hat plus 5 along V hat minus, you then have the position of O to A, which is 15 W hat plus 30 V hat, which then gives you 8 U hat minus 9 W hat minus 25 V hat. So that is this vector. And if you can find the magnitude of this vector, then we have x. So x is the magnitude of A to P vector, which is, as we know, the dot product of it with itself. So I'm just going to have this here, dot product with itself. Which will then give you, I could break this down and write it as 8 U hat dot, this guy here, minus 9 W hat dot, the same thing, and then minus 25 V hat dot, the same thing. whole under root. So, of course, you now have to account for all these dot products. And instead of having to keep looking at the figure, we can just write down on the side that u hat dot v hat is 0, w hat dot v hat is 0. That's basically looking at this and this and this and this. They are 90 degrees apart, while u hat dot w hat is equal to cos of theta. Okay, so we just have to keep this in mind. When you now do this, you will then get 8 times 8 u hat dot u hat, that is just 64. And then you have u hat dot w hat, which is cos theta. So you have minus 72 cos theta. And then you have u hat dot v hat, which is 0. So that vanishes. Okay, and then you have minus 72 w hat dot u hat, which is again cos theta. And then 9 times 9 w hat dot w hat is 81. So it's plus 81. And then these two vanish. You keep doing that, and you will get minus 25 times 8 v hat dot u hat is 0. 25 times 9 v hat dot w hat is 0. 25 times 25 v hat dot v hat is 65. Sorry, 625. And that's it. So now you have square root of 770 minus 144 cos theta. A little bit of busy work, but as you can see, by simply defining a vector as we did, we are now able to calculate this distance x. And in this way, if you have the related position of these helicopters and a target location, you can define what should be the cable extension so that you can achieve it for just this one helicopter. Now, to do it for y and z, you can pause the video and try it yourself. I highly recommend doing that because I'm just going to show you the answer now. Okay, so what we've done is we defined this vector and then we found this magnitude. In the same way for y, you want to define this vector, and we do that by defining, as shown here, the position of P is the position of B plus, the position of B with respect to O plus the position of P with respect to B. Okay, that's what I've written here. And we're after this guy here. And so we know the position of O to P as 8 u hat plus 6 w hat plus 5 v hat. We've defined that before as well. That is equal to, what is the position of B with respect to O? It is just 30 along v hat plus this guy here, which is what we're after. So then you write it here, and then you do the same thing with obtain the magnitude. Do that thing here. And you will then see that you get this as your answer if you go through all the steps. Again, keeping this handy so that you don't have to keep trying to look at the figure and figure it out. You could do that as well. Just make sure you don't make any mistakes. And then the third one is the position of, well, I guess I wrote it as C to P. So that is this vector is what we're after. So we can write it as this vector is equal to this vector plus this vector, right? It's all in 3D. And so you have this relation here and you go through the steps and you get this as your answer. Okay. So I hope that this is a good review of all things vectors. In the next session, we're going to look into differentiation and how it relates to one-dimensional situations and cases where your vector itself is changing and so on.